Well, thank you very much. I'm very honored. Um, Nero and Professor Desai, I'm very honored to be here. And Pars, who did the connection and the link, obviously. So really welcome everybody, and I'm very honored to be here. This is my first time in India too. So what a welcome. Okay, not that one. That one. Okay. I've been introduced already. You already know that I'm a geologist and I study the planet Earth. And you know that I'm coming from Israel. But what you don't know is that I was born there. I was born in Argentina and not in Buenos Aires, in a very small town close to Chile, close to the mountains. And then when I was young, I emigrated to Israel, where I did my initial studies. Then I continued up north and I continued into Switzerland, where I implemented the lake studies, lake research into my knowledge. And then I continued even a little bit more north, and then I implemented the marine knowledge, okay? So from sedimentology to a lake to marine, I wanted to go more north, but there is nothing more north than Norway. so then I went back. Then I went back to Israel in 2011, where I established where I established my lab, basically. And what I do is basically studying the bottom of the ocean or the bottom of the lakes. And I will explain you why I do that. And one point doesn't help in the map. What you need is many points in order to better comprehend the environment. One point will tell you a story, but it will not tell you the complete story. The more dots you have, the more you can interpolate between the information and better understand how basically our planet works, okay? And my main motto for that is basically to understand climate change, present climate change, by searching the past. It provides the clues to understand the present and the tools for modeling the future. I'm not a modeler. I don't know what the future may hold, but I provide the modeler with the information so he will model, okay? And this should be a video. What you see over there, basically, our planet, a video of our planet for outer space, taken from the ISS, which is the International Space Station that you can actually see sometimes in our skies. And by the way, so you know, you have an app that you can download in your phone and you can see what they are saying and you can chat with them. It's pretty cool, by the way. You can put ISS in your in the phone. But what you see here is what you see in the planet is that you can see, let's leave it like that. Okay. But you see, basically, what I want to show you is that you see many colors. You see white of the clouds or the ice, or you see the dark of the ocean. And what you see, leave it at that. And you see many, many, many dots, okay? The dots of basically us. Us, we are a very powerful entity in the planet. We have conquered everywhere. From the top of the sky, basically the ISS is one of our entities, to the bottom of the ocean. We are just everywhere. We have found our imprint and our footprint everywhere in the planet, from the top of the Himalaya, okay, to the bottom of the ocean. Everywhere there is a signal of human presence in the planet. So if we have a presence in the planet, probably we have a presence in the climate of the planet, right? Now, what you can see also, this green, okay, this is the aurora on the northern or southern pole. But what you can see very, very nicely is that layer which it's invisible for us, and we take it for granted. We are living in that layer. This is our atmosphere. But the atmosphere is the only little thing that protects our planet for being the way it is and not converting it into Mars or Venus or another kind of entity in the planet, in the world, in the cosmos. So it's the only protective shell. And that protective shell is the one that we need to keep. And we need to hold it because it's the one that keeps us alive the way we know it. So what you see here, that there is a very critical connection between Earth and climate. And what you can see is the last 60 years of evolution of climate, and slowly, every time that you see reds, it's a warming trend. So you see how slowly the northern hemisphere is getting warm, while other parts of the planet are getting colder. And this is the last, I think, from 1880 until the present, kind of. So you can see a very alarming trend in climate warming, mostly happening in the northern hemisphere. My question is like that. Okay, we all know, we read it in the news. The climate change has a very big PR, let's say, public relations, right? But did we experience such temperatures in the past? Okay, this is my question. How do we know that? So we definitely need to go to the past. Now, when we are searching the past, this is the last 20,000 years of climate change. And what you can see over there is temperature difference in degrees, temperature difference from the present. Okay, it's like a difference from the present is plus minus now, right? And what you can see is a trend going down for 20,000 years. But my question is, okay, so we are talking about climate change, so there is a warming trend, right? But I want to know, it was even colder when we go back, or even warmer, I don't know. So we need to go even far in the past. And in this case, I go 5 million years to the past. I can go to the past, to the beginning of the planet, right? But I go 5 million, I stop over there because this is the world that it's similar to the conditions that we have now, in the way that India is here, Himalaya is starting to form, but is there. The conditions, it doesn't look like a different planet. So the climate state of the planet, it should be some kind of similar to the one that we have today, according to the models that we know. So what we see is that even 20,000 years ago, we have a very cooling stage of 5 degrees below what is the present. And this is a mean, okay? A mean 5 degrees. We did experience warming trends in the past. In the last million years, you can see the scale is varying, okay? In the last million years, you have several peaks of warming trends. And if we go from 1 million to 5 million, there is a really big mama trend, okay? Going very high, even higher than today. But by the way, we are now breathing the same carbon in the atmosphere that we were breathing 5 million years ago, okay? And we are getting into that temperature. So we are getting into a state that was, last time it was 5 million years ago. And I want to go to that 5 million years ago. Why? Because that 5 million years ago is exactly like now, but without the presence of us. And then I can understand how climate works without us influencing it, right? So what I need to do, I need to take some kind of a time machine, right? Okay, let's sit over there, let's push the button and let's go back 5 million. Actually, I would like to go even further, but let's say we want to go 5 million years old. But what if I tell you that actually such a time machine exists, okay? It exists, and we have it in our backyards mostly. It's a pipe, okay? It's not so complex. But, and we have it everywhere. A time machine is our natural system. And we can go back in the past several decades, hundreds of years, and we can check for dendrochronology. What is dendrochronology? We cut a tree and we check all these tree rings. With what we need, basically, some kind of a continuity of the natural system. So for a continuity, we need a system that holds that continuity. A tree will hold the continuity since the tree was born until the tree dies. By the way, we don't cut the trees anymore, okay? We just drill a small hole and and leave the guy in peace, okay? We don't do that anymore, but this is an example. But then we can know how the tree grows during wet periods, dry periods. We interpret that. This is not what I'm doing, there are people doing that. But then we can go far in time, 5,000 years ago. How do we do to go so long? I mean, we don't have 5,000 years old trees, or maybe we do, but we don't know about them. So what we do, we go to the geological record. Okay, the tree that is growing in the backyard, we can drill a very small hole, obtain like a small, long record. Then the tree that is in the houses, the tree that is under the lake, and so on. We date it, and we make a continuous go back as much as time. We interpolate all the information, and together we go as far as we can. And we have reached, I think, 10,000 years ago, or even more. But what if I want to take? I didn't reach yet to the 5 million. Yeah, in my machine I want to go to the 5 million. So I want to go even older. And if I want to go older, I can go to the ice cores. I take a plane, let's go to Antarctica. I need to put, the right equipment. And then I will go over there and take a core from Antarctica or from Greenland. I need a lot of ice, many ice, as much as possible. By the way, they do it also here in the Himalaya, but it's different. But then what I see is layers of ice, packed ice, one after the other. And again, I have this continuity. Is cyclicity. Everything is cycle in life. Everything is continuous. Okay, one layer comes, another will come later. Okay, but what do I do? Basically, it's not what the scientists do. They check for the little bubbles that they are in the ice, and these little bubbles get compressed through time, but you can still check about them. Now, this bubble is basically a piece of oxygen and carbon from the atmosphere, which is trapped in the ice. Simple as possible. You just go, take with the right system, obviously, and analyze what is the composition of the atmosphere at a specific point in time. And then you can go basically 800,000 years until Antarctica was free of ice, or even older, okay? And then you can get this graph, which is hot and cold, hot and cold, hot and cold. That's general what you see over there, without getting into the little details. Again, I didn't got into the 5 million, yeah? I am stuck in the 800. I want to get into the 5 million. So I need to get deeper, older. The deeper I go, the older I get. And then I come to the marine sediments or to the lakes. Marine sediments, all the rivers, or the Ganga, the Brahmaputra, everything goes into the ocean, and eventually it doesn't go out. Okay, there is this sentence I saw in a movie. How do you take a drop of the rain and put it in the ocean? Just leave it and it will get there. And along with the drop of water, you will get dust, you will get everything will go there and will stay. Hopefully, as much as possible, if the ocean is deep enough. So what we do, we take a drill ship. In this example, this is the JR, which is non-functional already 2 years. India is a member of this organization. I was Israeli representative for the IODP, the International Ocean Discovery Program, and India is a member. I think is still a member of that program. It's a very good program. They had until 3 years ago 3 ships. The JR was one of them, Challenger, another one, and Chikyu, owned by Japan. Chikyu is the largest ever built scientific ship in the world. It's like being in the best possible laboratory in the planet, basically. You have everything that you need, everything. Because basically each time that you go for a mission like that, you leave the port and you come back to another port, or maybe to the same, after 2 months. So basically you're doing a scientific cruise of 2 months completed, and very intensive, 12 hours a row. So basically what you do in the ocean, you get to the drilling site that you plan to drill. You need to know exactly how to get there and why you choose that site and not another one. There is a lot of planning for that. It costs a lot of money, so you need to plan well. And you obtain the sediments, which basically it's this mud, basically. And now we scientists, we are like little kids playing with mud, basically. But playing with a very precious mud, because it costs a lot of money and it's the only mud that you get from that point. And what you see, you think that mud will be mud, but basically mud, you see the colors is changing from black to red to gray to green to every color means something. There is a cyclicity. This will be top and there will be bottom, you know, one next to the other. And there is a cyclicity of colors and a cyclicity of mud. And it holds the secret that you need, okay, for understanding. And basically all this, once it's taken, it's very well protected with avoiding oxygen and everything, you know, avoiding deterioration, and it goes back on land into very big cooling rooms. The one photograph over there is the Bremen Core Repository. I think it's the largest in the world, which is in Bremen in Germany, and it holds half of the ocean basically over there. There is another one in the United States, and there is another big one in Japan, and probably in India there is also. Holding all this. You need to really take care. It's not that, okay, you already took the corner, you need to take care about it, right? Now we have drill everywhere. And the ocean pretty much looks like that. I don't know how to say that in English, but you know, that thing. So it's pretty much drilled everywhere, but still you have places that were not drilled, and we still basically don't know nothing about the ocean, which is 75% of our planet, okay? We have more knowledge about the space because we watch it rather than from the ocean, which we are living on it, okay? We have very lack of knowledge. Once in the lab and after storage, we take the tools, we sample the sediment, and then we check for physical, chemical, and biological markers. And then each one of them, and there are many small subsidiaries of each one of them, will tell us a story. More that we can interpret for proxies. More rain, less rain. More temperature, high, low temperature, high temperature, low temperature. Change in the chemistry, change in the biology. You have this type of animal and that you have another type of animal. And then what is very important, that this is changing through the core, which is this, you convert the core into time. Okay, it's very important to know, because eventually we want to know, okay, this change happened X thousand years ago. So you need to know that thing, okay? And there are several methodologies to know that. But one of the systematics in the ocean is this little animal, which is called foraminifera. It's a plankton, basically, that you don't see. It's very tiny. It exists everywhere in the water on the planet, everywhere. And it covers all the floor. You don't see it, but it's everywhere. Even that by mistake you will inhale water when you're going to the beach, it will be there. Okay, it's everywhere. But it's okay, it will go out. But what I'm saying, that this little animal, it builds a shell. And the shell basically is like this little bubble of the ice. The shell will represent the water in which that animal lives. So what we analyze that shell, eventually when you have the layers, that animal dies very quickly actually, and then in the sediment you will take it and analyze the carbon, the oxygen, and it will represent the ocean, which represents the atmosphere which is above it. So eventually you go to the same kind of cold warm, and then you can go further in time, millions of years. And now we get into the 5 million, okay? Luckily we are there. But what? And then we can understand things like why he's still chasing. I hope that you know that movie, right? So, but there is something absent over there, right? I mean, not only there are holes in the ocean, but there is something very important. We lack information about the continents, right? You don't have those dots marking the continent, but we actually do. And these are the lakes. And the lake is like a small ocean, basically. Sometimes it's easier to get there. You can take a small ship, not a big one. You can even take a small boat, not a very big ship. So let's say financially it's much more easy, but it's more complex because the changes occur very quickly. Okay, and sometimes the lake will disappear. They don't stay for many millions of years, not all of them. So a lake is an integrative system of everything that happens in the environment. From vegetation, from volcanoes, atmosphere, whatever, eventually comes back into the lake, the same way I explained for the ocean, and will be stuck in the sediments. Then we come and take the cores, which basically the sediment core is like a pipe filled by the mud, and then as also Dr. Parr said, we will have all that, right? In continuity. So here I show you another movie, and I hope this one will have the music. It's a good music. And I give you an example here. So what you see here is an example from Lake Chala, which is in the Kilimanjaro. Sorry, the map should appear later, but never mind. This is a 24 hours movie. I was there for a month and a half. Sometimes we use a boat, sometimes we use a platform. You see a platform. You need to build a platform. It takes you like at least a month to build a platform. You need people to read. It's not so easy. You think it's easy, but it's not. It's absolutely not. And you always face challenge in science. But challenge is good because when you are facing challenge, you become better. And the next challenge will be easier for you. And then you will have another challenge, and then you will overcome that. So challenging is good, okay? Sometimes it's annoying, but challenging is good, you will learn. But during that, once the platform is in place, the work is done 24 hours a day. You want to profit as much as possible. You do shifts. I was in charge of the night shift. And the Kilimanjaro Mountains is in the back. And I'm sorry that you don't see the movie so well. The Kilimanjaro mountain, this is a caldera of the volcano. One part of the Kilimanjaro is huge. So this is a small part of the Kilimanjaro. And it's a beautiful setting. It's really amazing setting. And it's very distant. So it takes you at least an hour when you finish your mission. You need to go and sleep. So it takes you an hour. So you sleep. No, you don't sleep so good because you need to eat, you need to sleep, until you get there and everything. So, but eventually you get the gold mine, which is what you want, the sediments below that lake. And there is a reason why we need the lake. I did it in 2016, and we went back eventually 250,000 years back in history. And yeah, this is, well, now you see the movie. With the music. Now you see it. It's a good one, told you. And you can see the Kilimanjaro in the back. And you see now, this is the science team. This is the technical team. The technical team were South Africans managed by Americans. And we were international team of Belgium, I am Israeli, a German, and a Dutch, I think. So we need to communicate. And the Tanzanian, there were Tanzanian over there too. The lake is exactly in the border. And we had a lot of problems. It got stuck and whatever, but eventually we got a pristine long core of 400 meters going back in time to 250,000 years with a 98% of recovery. 98 is pretty a lot because you always have holes, but it's very good. So Lake Chala is over there, but we need many cores in order to understand the spatial distribution of climate. And one of them, some of the cores that I'm working, actually the dots are in the locations. So in Argentina, in the bottom of southern part of Argentina, in Lake Chad, in Renuka here, and in Yemen. This is the project that Dr. Parks was working on. Sometimes I cannot go to Yemen because of the issues, but a professor in the United States took the course already more than 20 years ago, and together with him, we did the work. Sometimes you go to the site, sometimes you profit, of course, that they are already taken. You don't really need to go to exotic places to do that, okay? Or dangerous places. Somebody already did the work and took it. So eventually, as I say, you take the biological, chemical, and physical properties, and eventually you produce a comprehensive data set of the climate through time. And the more I learn about the past, the more I have clues to understand the present and to know, to foresee the future. But this is not done only by me. This is by a group of people that are in the lab, that form part of that group. There are more than 20 people, postdocs, master students, and bachelor students, that each one is working on a different project in a different lake or different systematics, and together they work on producing a more comprehensive information. So I wanted to thank you. I hope that I wrote it right. That's the University of Haifa in the top of the Carmel, and we have, again, a lot of opportunities to students eventually when you want to foresee later stage studies, you can come because we have a lot of opportunities for you too. Thank you.